Alright, let's go ahead and start today's lesson. This is going to be out of section 5.5, and it's talking about U-substitution, which is a technique for integration. So hopefully you take a look at the opener before you started the video. So if we take a look at this equation here, y equals x cubed plus the inverse tangent of x, and we want to know what the differential dy is, we can start by simply differentiating both sides. So we'd have dy dx is equal to 3x squared plus 1 over 1 plus x squared. And if we're looking to isolate dy, we essentially just multiply both sides by our differential dx. So we'd have the quantity dy is 3x squared plus 1 over 1 plus x squared dx. And this idea of separating out the differentials is going to be important for our technique of U-substitution today. All right, let's start out with kind of this introductory example here to kind of get us understanding why we need to do U-substitution. So if we take this derivative here, this is something we would have to use our chain rule for because it's a composed function, sine of some stuff here. The stuff is x cubed plus 1. So when we take the derivative, we have our derivative is equal to cosine of the stuff times the derivative of the stuff, which would be 3x squared. So we could just write that as 3x squared cosine of x cubed plus 1. And that's not too bad. So now if I were to ask you, what's the antiderivative of 3x squared times cosine x cubed plus 1? That wouldn't be so bad because we just took the derivative of what gave us that. So we could just work this backwards and say, oh, that'd just be sine of x cubed plus 1. No big deal. But if I had given you that antiderivative to start this page, I don't think we'd have the right skill set yet to be able to do that. It's much too complicated. Notice all of our antiderivatives that we've been doing so far haven't had any sort of this composition of functions. It would have been just cosine x. And it probably wouldn't have had that 3x squared out front either. So what we need to develop today is a strategy to be able to do these more complicated antiderivatives so that we don't have to know ahead of time, like we did on this page, where it came from. That process is called a U-substitution. So we'll call them U-subs for short, and they're used to change an integral into a simpler one, especially when the integrand of the integral has a composition of functions. The way we're going to rewrite it to a simpler integral is by using a clever substitution. So we're going to have to think about it. We can't just choose anything in order to rewrite the integrand. So looking at this first antiderivative here, sorry about that. Looking at this first antiderivative here, we notice that we've got 3x squared times the cosine of some stuff, right? Again, we have a composition of functions here. Whenever we have a composition of functions, that's always a good guess for what we're going to want to substitute out. All right, so we're going to say here, I don't want to have x cubed plus 1 anymore. Let's let some other variable, and we use u, hence the name u-subs, represent that composed quantity. So in this case, x cubed plus 1. If we were to just go ahead and make that substitution now, which we really don't want to do, so don't bother writing this part down, we'd have 3x squared times the cosine of u dx. And we've got an issue here. We now have an integral in terms of x and u, and we're taking the integral with respect to x. This doesn't all match up. It's got to be one variable in the integrand, and it's got to match with the variable that we're taking the antiderivative with respect to. So we're not quite ready to go here because we don't have enough matching going on. So let's take a step back here. Let's see if we can convert everything else to things in terms of u, right? The idea is we want to write this in terms of u, hoping that when we do that, it's going to be easier. So if u equals x cubed plus 1, let's figure out what du equals. This is a lot like our opener now. hopefully we can see that that would be 3x squared dx. And now I guess we kind of got lucky here, because if we take a look, we already have a 3x squared as a factor of the integrand with a dx on the end. So we can kind of swap out the 3x squared dx for just a du. So now we can go ahead and write this part down. We can rewrite our integral as the antiderivative of cosine u du. The cosine u came from our cosine of the stuff. The du came from the 3x squared dx. Now this is a pretty simple antiderivative to do. Antiderivative of cosine is sine plus our constant of integration. And since our integral was in terms of x, I suppose our answer should be 2. So we'll just go back and swap out the u for what it really is. It's sine of x cubed plus 1, still plus our constant. And that's the general strategy for doing a u-sub. We're looking for the composition. We kind of make that our first guess for what our u is going to be. We figure out then what our du would be. And hopefully it's already sitting there in the problem. We can swap everything out and we're good to go. Maybe it won't be, and we'll see what we have to do then in just a second. But it allows us to actually take this antiderivative. So let's do a couple of examples here. All right, here's our antiderivative of cosine x times the cube root of 1 plus sine x. So if we look for the composed function, I see this 1 plus sine x, because that's where we're taking the cube root of. So that's a good guess to start for what our u might be. So we will let u equal 1 plus sine x. Then du is just going to be cosine x dx. And again, it looks like we got lucky here. We already have cosine x as a factor of the integrand dx. So we can just go ahead and rewrite this one. Have the antiderivative of the cube root of u du. Remember, cube root of u is just u to the 1/3. So we can go ahead and take our antiderivative in terms of u. That'd be 3u to the 4/3 over 4 plus our constant. And then let's make sure we put it back in terms of x. So we'd have 3 times the quantity of 1 plus sine x to the 4/3 over 4 plus our constant of integration. Okay, let's take a look at another one. Example 2. We've got the antiderivative of the natural log of x raised to the 4th power all over x dx. Again, it looks like our composition here is the natural log of x because it's being raised to the 4th power. So let's try that for our u. We take the derivative, separate our differentials. We see du is 1 over x dx, which we have. Maybe we don't see it right away, but I think by now we're probably comfortable with seeing this as 1 over x times the natural log of x. So there's our composition. There's our factor of 1 over x dx. And we can just kind of finish this one out just like all the other ones. Antiderivative of u to the 4th du. That's going to be u to the 5th over 5 plus our constant. Put it back in terms of x. Natural log of x to the 5th power over 5 plus c. So hopefully we're getting the hang of these kind of basic ones here. We've seen kind of 3 of them now. Let's take a look at one that's a little bit different. All right. Looking at our antiderivative, again, we're kind of looking through it for where the composition is. I see secant squared of x cubed. So I'm going to try my u sub to be x cubed. So du is going to be 3x squared dx. And here's where it's a little different. We don't have a 3x squared dx. We've only got a 1x squared dx. So we can use one of our antiderivative properties to kind of help us rewrite this a little bit. If you remember, we're allowed to pull out constants out in front of the integral because it doesn't really change the value of the integral. We can also kind of use that fact to do this little trick. I don't want to change the value of my antiderivative, but I want to change the way it's written. I want it to be 3 x squared secant squared x cubed. But I can't just multiply the inside by 3 because that's going to change it. So to balance it out, I'll just multiply out front by 1/3. Basically, I'm multiplying by 1. We still have our composition of x cubed. We still have, or now we have, our 3x squared dx. And we can finish this problem out just like any other U-sub problem that we've seen already. We'll have 1/3 times the antiderivative of secant squared u du. Hopefully we remember that the antiderivative of secant squared is tangent. And then we just put it back in terms of x. So 1/3 tangent x cubed plus our constant. All right, last example. Notice here we have a definite integral. Now we're not doing just kind of general antiderivatives anymore. We're going to need a numerical answer. This is representing the area between this curve and the x-axis between 0 and 3. It's a number. So let's figure out how to do that. Okay, again, we kind of look for our composed function. There it is, cube root of x squared minus 1. So we'll let u equal x squared minus 1. Therefore, our du is 2x dx. Don't have 2x dx, I've just got 1x dx, so let's use that trick again here. We'll multiply the outside by 1/2, so I can multiply the inside by 2. And now we've got everything we need. There's my composed part, that's going to be my u. Here's my 2x as a factor dx, so I can rewrite that. And then when we go to rewrite this, here's where things get a little different with the definite integral. If we keep it as 1/2 the integral of the cube root of u du, notice what happened to our variables. Everything is in u, just like before. But we need to think about what that is going to mean about our limits of integration. The limits should also be u values. Previously, they had been x values, right? If we think about again what this means graphically, we're finding the area between 0 and 3 on the x-axis. We're basically changing this to an integral on some different axis, the u-axis, which we don't really need to think about what that is, but we should realize that, okay, well, 0 to 3 on the x-axis might not be the same thing on this new one. And in fact, we need to change them over. Now that sounds like it might be difficult, but lucky for us, we already have an equation that relates a quantity of x to the quantity of u. So when x was equal to 0 over on the first integral, we can just plug that in to see, oh, that's the same thing as the u being -1. So our lower limit of integration would be -1. When x was equal to 3 as the upper limit of integration on the first one, when we plug that in, we get u is 8 for the upper limit over here. And that's actually going to make these problems a lot easier. Because what we can see we can do is when we take the antiderivative of the cube root of u is going to be just like before, u to the 4/3 times 3/4 evaluated from these u values. And this is actually not bad because we're doing cube roots, and 8 and -1 have nice, easily available cube roots. We'd have 3 times the cube root of 8 is 2, and then we raise that to the fourth power, so that's 16. Minus, we evaluate at -1. Cube root of -1 is -1. To the fourth power is +1. And we get some nice simple arithmetic that we can do here. So we'd have 1/2, 3 times 16, that's 48. Minus 3/4, that's 45/4 times a half, so how about 45/8? I'm sure if I made a mistake, somebody will find that out and point it to me, but it seems okay to me. And we're done. We've got it down to a single area, single quantity, since it's a definite integral. And we never really had to go and do anything else with those values once we converted them to u. Just plug them in like normal. Take a look at the other examples here and see if you can work those out, referring back to the previous few examples to help you out. Again, you can kind of give you a few hints here. Look for the composed functions for your u value. So in that first one in the upper left here, that looks like it'd be a good composed function value. Sine of e to the 2t, that looks like it might be a good value there. Bottom left here is going to require you to remember a little bit about your trig antiderivatives, specifically your inverse trig antiderivatives. This is probably the hardest one on the page. We got to figure out what to do with that 9x squared. I'll let you think about that one. Last one here, again, composed function. Just make sure you deal with the limits. They're currently t values. You're going to want to make them u values. All right, these answers will be available in class for you tomorrow. You'll be doing a few more examples. Make sure you bring your book because you'll have some book work to do as well.